Bandwidth for changelog is provided by Fastly. Learn more at fastly.com. We move fast and fix things here at changelog because of Rollbar. Check them out at rollbar.com. And we're hosted on Linode Cloud servers. Head to linode.com/changelog. This episode is brought to you by DigitalOcean. DigitalOcean makes it super simple to launch a Kubernetes cluster in minutes. The DigitalOcean Kubernetes platform empowers developers to launch their containerized applications into a managed, production-ready cluster without having to maintain or configure the underlying infrastructure. They seamlessly integrate everything with the rest of the DigitalOcean stack, including load balancers, firewalls, object storage spaces, and block storage volumes. They even have built-in support for public and private image registries like Docker Hub and Quay.io. Developers can now run and scale container-based workloads with ease with the DigitalOcean platform. Learn more, get started for free with a $50 credit at do.co/changelog. Again, do.co/changelog. Welcome to Go Time, a podcast featuring a diverse panel and special guests discussing cloud infrastructure, distributed systems, microservices, Kubernetes, Docker, and also Go. We record live every Tuesday at 3 p.m. Eastern, noon Pacific. Join the community that's live with us in real time during the show in the Go Time FM channel and Go for Slack. Follow us on Twitter. We're at GoTimeFM. Listen live at changelog.com/live or subscribe at changelog.com/GoTime. And now on to the show.
Hello and welcome to Go Time. I'm Matt Ryer. Today we're talking about graph databases. Joining me, it's Johnny Borsico. Hello, Johnny.
Hello, Matt.
We're also joined by Jaana Bidogan. Hello, Jaana.
Hello.
How are you?
Good.
Welcome back. It's been a while.
It's been quite a while.
Yes. Well, it's good to have you back. We're also joined by a special guest. It's only Francesc Campoy. Hello, Francesc.
Hey, how's it going?
How are you?
Pretty good. That was a decent pronunciation of my name.
Oh, excellent. Thank you. That means a lot. Well, I'd like to start with one of the first questions that gets asked every time I mention you is from Pontus on Slack asks, when is Just for Funk coming back?
Eventually.
Great. It's eventually cool.
Eventually coming back. Maybe next year. Maybe.
Do you need help?
I need extra time. That's the only thing I need. But now I finally moved to a new house and everything. I'm settling down and I will have a little studio, so I'll be able to start again. I now just need the energy. So, couple months of relaxing and then back.
Great. For anyone who doesn't know, which is probably nobody, there's a great video series that Francesc does called Just for Funk. I'm fine that you picked that name. I suggested Go Funk Yourself. That was rejected. I didn't like that one.
Yeah, back then I used to work at Google. Not sure how that would have been accepted.
Funk that.
Another one that got rejected. So today we're going to talk about graph databases, and this is a really interesting area, and it feels very new, and we're going to dig into that a little bit more. But maybe we could start off with a simple overview, Francesc, of like what you're doing, and then we can go into what actually is a graph database.
Yeah, so I can talk a little bit about how I got involved with graph databases. So after I left Google, I joined this company, Source, where I started doing code analysis. And when you think about it, like if you think about how you parse code, you end up with a tree, right? Syntactic tree. And the idea is once you start adding annotations on top, like this function is calling the code in there, or this variable was declared up there, or this is the type of whatever. You start having like a graph, right? And then you think about how are you going to store this, and you look up relational databases, and it's a bad match. It doesn't really work. It's super hard to do. And as soon as you start adding more things, it just breaks. The schema needs to be very, it's too strict, right? So then you go into NoSQL databases, and then you have the issue of how much do you replicate, right? Like, do you want to replicate the same information over a bunch of times for performance, but then you need to take into account the consistency, or do you want to put everything into little pieces, but then it's going to be super slow? And that's when I started looking into graph databases. And, you're right, it sounds like it's somehow new. That said, how old do you think Neo4j is?
Ooh, that's a good one. Johnny, what do you think?
I'd say at least 10 years.
It is, if I'm not mistaken, 19 years old.
Wow.
Yeah, so they've been going at it for a while.
It can nearly drink.
Yeah, I mean, in Spain it can definitely drink. Yeah, yeah, no, and so it's not a completely new technology, but it's something that has been evolving over time, little by little, and I started looking around, and there's not that many graph databases. Actually, like pure graph databases that have a graph layer. There's a bunch of them. There's like a bunch of different competitors, etc. But the problem is that storing things as a graph is actually something not that easy to do, and it's something that brings a lot of flexibility, because the idea is that instead of having to, it's like if you think about a graph, let's say, Twitter, the people that you follow, and like the tweets and like the tags and hashtags and all that stuff, right? If you store that in a graph database, the same way you would draw it in a whiteboard, that's what you store, right? You store nodes and you store relationships, and that's pretty much it. As soon as you need to start thinking about, how do I model this so it fits my database? You're adding complexity from the point of view of like the developer. Like, you need to think about these things, right? Which is an important cost. People do not take that into account, but complexity that you add to your system means that once you're going to start debugging, it's going to be harder to debug because there's extra layers of abstraction. And then on the other side is also performance-wise. The way you're going to be able to retrieve things, if you need to do transformations, like if you think about a relational database, and we have like people that follow people, right? If I tell you, find all the people that follow, like all the people that I follow, and then their followers, and then their followers, or something like that, right? Like, you're gonna go quite deep. It's gonna be a bunch of different requests, and this is what people call the N+1 problem. The idea of, if I fetch something and then I want to fetch something related to those things that I just fetched, you have to do a query. Start with that data set, and then for every single item in the data set, do one more query. And it keeps multiplying. So it doesn't really scale. So, it's like the idea of graph databases is solving that problem specifically. And so I started looking around, and I decided to join Dgraph. Partly, they're running Go, which is kind of cool. I think that people might like Go in this podcast. And also, it's completely open source, it's distributed, and it's also in San Francisco, which is nice because I didn't want to travel that much.
So that's interesting then, and I want to talk more about this later, but you said it's distributed.
Yeah.
Because as I understood it, one of the things that makes graph databases quick is that it's kind of all stored in the format that it doesn't get transformed very much, does it? It's kind of stored in the format that you then use it with. Does that make sense?
Yeah. So the whole idea, there's this term that people like to throw around, even though most people do not really understand what it means. It's called index-free adjacency. And index-free adjacency just means that when you there's a very good metaphor that I like to use. So, in index-free adjacency, imagine that I'm Francesc and I'm trying to go to someone's house. I just know their address and go there, right? That is index-free adjacency. You just have all the information from the beginning. While in normal databases, the way it's going to work is I have a key that allows me to go check it out, where this information is, and then you go find it, right? So it's more like I go to some place like a phone book or something, where I find this, the name of the person, I can find the address, and then go get it, right? So that extra step, that is a little bit the main difference of how things are stored. But at the end of the day, the way we store data, it's key value, right? Like, it's just a key value store that is extra fancy with a bunch of things on top and Raft consensus protocols and things like that, right? But the way we store things at the end of the day, just key values. And the distributed part of things is the fact that, many databases, Neo4j is one example, in order to be efficient, they need to store everything in the same machine, right? At Dgraph, what we do is instead we partition dataset by the predicate, right? So say there are many predicates like name or age or friends. That information is separate. So we're going to store it in potentially different machines. Not necessarily, like you can run everything in the same machine, but it could be potentially in multiple machines. And the idea is that by separating the data like that, no matter how much data you're fetching, the number of phone calls, I was gonna say, the number of network requests that you're sending is proportional to the number of predicates that you're fetching, not the amount of data. So it scales really well. Otherwise, if you end up partition in any other way, at least the ones that we've tried, you end up with, as you go with more data, you end up having to send queries to all of the computers that are involved, and then that kills performance again.
Can I ask a more fundamental question? Because I think I'm super unqualified to be on this podcast. So compared to, for example, like column-based DBs, like what is the overall, underlying storage structure for a Graph DB in the same node? Like let's say everything is just like on one machine.
Yeah, so it's kind of cool because we use an open source project that was also created by Dgraph. It's called Badger. And it's the project that gives name to our mascot, which is Badger, Diggy the Badger. And this is just a key value store, right? So you're storing, it actually works with, so it's a key value store. So you could think about SSDs and things like that, like sorted string tables and all that stuff that we use at Google. But the idea is that from a high level point of view, you just have keys and values. The way this is actually implemented internally, it's an LSTM, which it's a log structure tree. What it was? Log structure tree merge. Yes, merge tree. I always mix it with LSTM with long short term memory, which is an AI thing. So I mix everything. But yeah, like this structure, what it allows you to do is to have a very good insert time and also very good retrieval time. So it's just a different kind of tree that we use. And if you ever heard about RocksDB, it's somehow similar to RocksDB. The two biggest difference is one, the values are not stored inside of the tree, which means that it's more efficient from the point of view of storage. And also when you're iterating over keys, it's much faster because you don't need to fetch the values. And then the second one, which is more important, it's actually written in Go. And that for us was very important because otherwise we had to use Cgo. And Cgo is great, but not really necessarily performant. So it was actually important to be able to have something that was working natively in Go. Mm-hmm. But yeah, it's just a fancy key value store at the end.
So one of the examples we've already sort of touched on is sort of the social graph, right? Because that's an easy sort of thing to wrap your head around. I'm interested to hear what some of the uncommon sort of examples that you've come across, right? Or Dgraph has come across, maybe in its customer base, basically for using this type of technology. What is it really, really good at beyond just social graph?
So yeah, social graphs is the traditional example because as soon as you talk, about graphs, people's like, Facebook and Twitter and all that stuff, which is great. Like it actually works pretty well for those use cases. But in general, that is a class of knowledge graphs, right? Like graphs where you're storing information. So for instance, Dgraph actually comes from technology developed at Google. I think that internally the project was also called Dgraph, which is weird, but it's okay because Google never uses the internal name externally or something like that. So it was cool. But yeah, like it is the same technology. And the idea is when you're storing information for, like movies and actors and a lot of stuff, like if you think about I think it's called one box, which is when you search something and you have on the right side of the search, like this extra information telling you like, the actor and the movies they've been in and stuff like that, that actually is served by a graph, right? So the idea is in order to store that information and being able to retrieve things quite easily, graphs are the best way to do it. But then on top of that, that knowledge graph could be something that changes really fast. We've seen people doing knowledge graphs or it's more like a visibility layer more than anything on top of Kubernetes, right? So you have if you think about Kubernetes, you have services and pods and all of these things. They're all related in many different ways, right? Like there are tags, there are like traffic and like services sending things around. You can visualize that inside of Kubernetes, inside of a graph database, and then query things like, hey, what are the things that could impact this service, right? If this service goes down, or the other way around, right? Like if this service goes down, what pieces of my system will be impacted? And that is a graph problem. This is actually an open source project created by VMware. It's called Purser, P-U-R-S-E-R, Purser, I think. But yeah, and there's many others. There's things like actually geographic graphs. So we have geolocation. So you can do things like find all of the hotels that are, at less than 50 miles from downtown of San Francisco, and then from there do more graph stuff. So you can go quite deep into finding things about your data set that otherwise it's just very hard, right? Because if you think about all of these queries, you could definitely do them anywhere, right? Like you could do them on a normal database, on a relational database. The problem is that it's going to be way, way slower. So it's just, I don't know if you've ever used BigQuery. With BigQuery, you end up like writing queries that run across terabytes of data. And it's not about the fact that it's easier to write. It's just that short developer loop it's just much better. You get the feedback and you keep on playing. While, if you need to wait for 5 minutes, it's going to be way, way slower and more painful. And then, one other data set one other use case that we see very often is, since there's no need for a schema, you can actually integrate a bunch of different data sets together very easily. So data set integration or data set unification happens pretty often. So if you see, like, imagine you have a really large, telecom company that has been acquiring different companies. And for every single one of those companies acquired, probably there's a user base, right? There's an account database with a bunch of different things. And what you want to do is being able to integrate all of those systems together into one. Graph databases are great for that. If you think about how would you do it with a relational database, the number of foreign keys that are going to be flying around is going to be pain, right? So that kind of thing is also very useful. It's very simple. It works really well.
So you talked earlier about indexes, and this is kind of doesn't have that same kind of pattern, because I was playing around recently with Firestore, which is the Firebase schemaless database. And if you do queries that you haven't done before, you actually get an error, and it says, I can't serve this because there's no index that matches the order of those fields or whatever the filter is you're doing. And so you kind of have to know in advance what you're going to be asking of this database. Is that different in graph databases because of its nature?
So not necessarily. The whole idea is indexes are not necessary to traverse relationships, right? So if I start from a given node, going around that node will not require an index. The place where you might need an index is to find that first node. The whole idea is that while you will not need indexes to traverse relationships, you might still need indexes to find those first initial nodes that you're going to use to start your traversal. And there's a bunch of different things. Like, for instance, if you want to find all of the orders, all of the products that have been ordered by a given user, right? All of that does not require an index, but actually finding the user from their username, that will require one. So you do have indexes, right? And those indexes need to be built. So they will not be built until you ask for them. But the idea of using Dgraph, I'm actually not that sure about all the graph databases, but for Dgraph at least, the way it works is that you start just you start inserting data. You don't care about the schema, but there's a schema. There's a schema that is being created as you go. And then if you try to do a query that requires an index and it's not there, it will indeed fail and tell you, hey, you need to build this. You click a button, now you have an index. And then the idea is that while you're developing, that schema is going to evolve over time. And then at the end, that schema is something that you're actually going to put in your source code, right? Say, okay, this is the schema that I'm going to be using. And then when you set it in production, normally what I recommend is there's a strict mode for mutation. So when you're putting new data, you can actually say, hey, if that data does not follow the schema that I already have, reject it, right? It's a much safer way to do it. for development, I think that free, like schema-less databases is great. But then as soon as you get in production, I'd be a little bit more careful with that.
I had the same thing. I used to do MongoDB stuff, and it was the same. Like when I first I couldn't believe that I didn't need to think about schemas. I can just do anything, and actually documents don't even have to look the same or even similar. And that freedom just felt so powerful. And once I'd built a few things, I realized I could really use some errors about now.
Yeah. So the idea for us, right, is that you can start with no schema at all, but we also have a type system on top. So the idea is you start adding things, and then you're going to say, oh, this node has this type, and this type is supposed to have these fields. It doesn't mean they have the fields. It just means that they should, right? So if you have a person, you could say it's supposed to have a name and an age. So then when you're fetching things, you're going to say fetch all the fields of type person or things like that, right? So you can actually have a type system on top, and that is something completely optional, right? So you can start from paying zero attention to the data you're storing in your database, see how it goes, end up with a schema, and then from that schema that contains all of the predicates or all the kind of information that you stored, name, age, friends, all of those things, then you're gonna go and say, okay, is this actually the type that I want? Do I need indexes on this? So like a username, I'm gonna find exact, or I'm gonna use hash to find these things, and then group those into types, and then you can start doing more like advanced things. And the cool thing is that once you get there, then you can present that we have a GraphQL layer. So then you can actually start sending queries in GraphQL to your graph database, which makes it so, front-end engineers are much, much happier when you tell them that they can use GraphQL instead of having to learn a new language one more.
How often do you think about internal tooling? I'm talking about the back office apps, the tool the customer service team uses to access your databases, the S3 uploader you built last year for the marketing team, that quick Firebase admin panel that lets you monitor key KPIs, and maybe even the tool that your data science team had together so they could provide custom ad spend insights. Literally every line of business relies upon internal tooling, but if I'm being honest, I don't know many engineers out there who enjoy building internal tools, let alone getting them excited about maintaining or even supporting them. And this is where Retool comes in. Companies like DoorDash, Brex, Plaid, and even Amazon, they use Retool to build internal tooling super fast. The idea is that almost all internal tools look the same. They're made of tables, drop-downs, buttons, text inputs, and Retool gives you a point, click, drag and drop interface that makes it super simple to build these types of interfaces in hours, not days. Retool connects to any database or API, for example, to pull data from Postgres. Just write a SQL query and drag and drop a table onto the canvas. And if you want to search across those fields, add a search input bar and update your query, save it, share it. It's too easy. Retool is built by engineers, explicitly for engineers. And for those concerned about data security, Retool can even be set up on-premise in about 15 minutes using Docker, Kubernetes, or Heroku. Learn more and try it free at retool.com/changelog. Again, retool.com/changelog.
Is there any additional cost of going completely schemaless because the indexes are going to be affected, and how rebuilding the index kind of works if you change the schema? Is this one of the reasons that on production you want to actually lock the schema?
So not necessarily. I'd say so. The idea is that you can change your schema as you go, right? It's totally fine. If you add a schema. If you're an index to something that didn't have an index, it will be computed on the fly, and it's fine. It's really fast also, but if you have terabytes of data, it might take a couple minutes. During those minutes, you will not be able to change your data. You will be able to only retrieve data, but not do mutations, right? Which is fine, but the idea is while you're doing the development, you're actually working normally with a smaller data set. And at that point, it's great because then you can click and it's basically instantaneous, right? So while you're developing that developer experience of schemaless, I really like it, right? It's somehow when you're writing code and you're writing in Python, the fact that you can just put things together and it just works, like that is great. But at the same time, when I'm going to production, I want to have a little bit more like rigidity and make sure that the schema is working for me. So I'm going to start adding things that will make it so if I do something wrong, which is totally possible, I will be notified, right? Some error, even if it's just a log or warning or something like that, is much better than silently failing, right? So that's a little bit the idea of why I want, like, I like the schema less and it's super useful. But once I'm in production, I'd rather be, it's like I'd rather be writing Go with a decent type system than be writing C, and I will end up having weird things happening if I'm doing something wrong, right? I have zero trust in me.
It really happened to me when I was working with document DBs. Since there's no schema, I would just end up having all these embedded types, embedded objects. So you can just end up just really doing a lot of things wrong, and if especially the references are referring large objects or whatever, everything kind of just gets into the database. So it's kind of nice to have that option to restrict it to a schema.
Yeah, I've had issues where after debugging for 10 minutes, I realized that the data I was storing had a typo in the name of the field. And that took me forever. So, I was like, that is the kind of thing I just don't want it to happen. If I can avoid that, much better for me. So yeah, that's why having a schema that's optionally enforced makes a lot of sense.
Yeah.
I'm trying to wrap my relational modeling head around sort of not having to have a schema, and that's proving quite hard for me. So how do you model relationships that are not just this piece is connected to this other piece by some sort of loose relationship between them? How do I model things like actual relationships, right? Yeah. Maybe I have an invoice with line items on it, right? This is kind of like a parent-child relationship. You can't have the line item just floating out and about. It belongs to something, right? It doesn't have meaning without the sort of the parent relationship, right? So how do you model these kinds of things? Or rather, do you have to throw that sort of approach out, the door, leave it at the door before you enter the world of schemaless and the world of graph databases?
I mean, you don't really need to get rid of all of the concepts that you have from before, especially if you're coming from a document database. If you come from a document database, imagine instead of having a document that is just a big JSON, you basically explode that into, instead of having an object that has name and age and then a friends that points to an array of people that have name and age, you're going to explode that into little facts. So you're going to say, this ID has name Francesc, and then age, whatever, and then friends is a list of different IDs, and then those IDs also have their name and age. So you're gonna break that into triplets, right? Like triplet is subject, verb, and object, right? So you're saying things about things, and that's what you store at the end, right? Like you literally store just that. So once you take that into account, you realize that all of the ordering that you had is gone. So then if you have something like an order with items and you want those items to be stored in some way, in a specific order, then you actually need to store that there, right? You need to say that the order, and you have different ways of doing this. You can create something like the way you would do it in a traditional relational database, where you're gonna have this item line table that points to both the order and the product that they have, and then also has the item number in there or something, right? There's a way to do it, but for us, you could do it just as a node. Itself is a node, which is something similar to what you would think about the relational database. Or you can also attach things. You can attach data to the relationships themselves. So you could say this item belongs to this order, and that relationship, you're tagging it saying it's item order number 1. So there's multiple places where you can store that kind of information, and the whole idea is very flexible, so you can do whatever you want, which means that you need to be a little bit more strict about you need to really think about how do you store this, and that's why having a schema is going to help you with those things. But at the end of the day, what we see is people modeling in the most straightforward way possible, simplifying as much as possible. And then they start sending queries and then start to see, okay, this is the performance issues I'm hitting. Because depending on the way you're storing data, you're gonna get more or less performance, right? So that's when you start tuning your database. But in general, I'd say that just storing the data the most natural way possible it is the best way to go. Because it's like when you're writing Go, right? Like you're not supposed to be thinking about cache locality right away. If you're doing that, your code's gonna be really ugly, right? Write code that makes sense to you and that makes sense to everyone, that is easy to maintain. And then if we need to find a hack somewhere to fix it and make it much faster, then let's do that then, but not from the beginning. And for data modeling, I would say it's the same. Find something that is obvious and very clear. And if that doesn't work, first file an issue, right? Let us know, because maybe there's an issue or something like that. But also at that point, we're gonna start looking into performance tuning and doing actual debugging and figuring out how much data are we fetching. Because sometimes it may be something as silly as like, oh, you're actually not using this index, and instead of loading one item, you're actually loading all of your database. That's not good, right? So that is the kind of thing that you need to look into as you're writing your thing. But data modeling should be as straightforward and as natural as possible. Because at the end of the day, you're gonna have to maintain that over time. So if you start getting smart, you're gonna need to be at least as smart as you are now in a month, which I'm not convinced I can. So yeah,
good point.
So along those lines, like, would you say, in my experience, you can go pretty far, with a relational database before you start noticing, that I didn't have the proper, index in the right column. Like you can kind of go far, right, before you realize, okay, I have to do something about this. I have a problem with my actual data and how it's being stored. Like it sounds like with key value stores, with graph databases, you kind of have to put a bit more sort of a forethought into how you structure your data, like where it goes, how you're going to shard and things like that.
It's the other way around. I would say that graph databases and document databases too, right? Like the fact that the schema is so flexible makes it so eventually, like you go for the simplest way. And if you then need to migrate to something else because you find something that was not taken into account from the beginning, you can, right? It is actually doing transformations in the data and everything. It's pretty straightforward. While if you think about relational database, right? Like I have this example of, you have movie and director. And what you're saying is a movie has a director. So what I'm going to do is I'm going to put in the movie a foreign key pointing to the director that directed that movie, right? And you're like, great. You start working on that. And then you figure out that, guess what? There's movies that have multiple directors. And now you need to refactor your database. And that is hard. Because the way you're storing the whole thing, it's going to be much harder to move out into different pieces. You're going to need to come up with a new concept, movie director or something like that. It's somehow in between, because now you go from one to many to many to many, right? So all of those things are way harder to do. While for us, if you say, oh, these are one to many relationship, and then it's like, oh, never mind, was many to many. It's literally just changing the type of the predicate in one place. That's it. Migration wise, I think it's much easier. The whole idea is that you get to make those decisions once you have the information that you need to make those decisions, rather than from the beginning and trying to get it right.
So that has a massive development advantage, because actually I think we sort of fool ourselves into thinking we can design these things perfectly in the beginning, and then then there's an implementation phase or whatever. And it's never like that. You learn so much by doing it that actually being able to be adaptive and to migrate the data and things becomes very, very valuable. Andy Walker in the Slack channel, Andy Walker's my new Twitter enemy. He was asking about what the switch between dev mode and prod mode kind of looks like. He asks, do I need a corpus of seed data that represents everything I care about, and then sort of clear that out in some way and snapshot it or something? What's the actual process there?
So the way I normally do this, and there's different options, but the idea is that while you're inserting data in the database, by default you can insert any data and everything will be accepted, right? So you start putting things in there, and it's going to be creating as you go a schema. So say I store something saying my name is Francesc, it's going to store something saying, oh, there's a thing called name, and it points to a type. And maybe it guesses a string if you send it as JSON, or if you send it as an RTF, it's going to say it's default. We don't know what it is, but you can store things in there, right? As you go, you're going to start tuning that up and saying, actually, name it needs to be a string. And not only that, but also going to need an index, right? Or then you get age and you get whatever, and you keep on adding more and more data as you go. The whole idea is that eventually you have all of the data that you need that is already in that schema. And then on top of that, you also have designed your database with all of the indexes that you need to do the queries that you're going to need to do, right? At that point, that schema that has been created automatically, you can literally copy paste it into your code and call it, like dgraph.schema. And now what you're going to do is when you start your program, if the database didn't exist, right, like it's a completely blank database, you're going to send that schema and then lock it and say, okay, from now on, this schema is not allowed to change. So if I want to send data that matches that, that's totally fine. But if you try to send data that instead of name, it uses first name, which is not something I'd said that you could use, it will just reject it. So that's the idea of, it is literally just when you start the database, you have this switch that says it's the serving mode, and it's serving mode is standard or strict. And the other one is completely nothing. You cannot mutate anything. You cannot change the data. It's like you get a read-only database. So it's somewhere in between. You can write things, but you cannot modify your schema.
Just because you mentioned read-only databases, is there any sort of like replication of data? Can I have like multiple read nodes, for example, and have like one write node, or?
Yeah, so that's actually, that's a very good point. So Dgraph, the D stands for distributed, right? So the idea is that you are supposed to be running multiple servers for every single function. So it is designed so it doesn't have any single point of failure. And it follows a lot if you think about how Kubernetes works. So you have multiple replicas, and those replicas in a group, they host the same information, right? They do the same thing. And we use Graph to decide which one is the leader. If one of them dies, we don't care. There's like, if you have 3 of them, right? Like one of them dies, you still have quorum, you have 2 of them, the database is going to continue working. And then once it comes back, it's going to be notified, hey, you're part of this group. This is the data that you should be serving, right? So it catches up. So the data will be replicated. But on top of that, if the amount of data that you have doesn't fit in a single machine, then you can start adding more groups. And then the data will be sharded across all of those groups. But again, they will have their own replicas and everything. So you're going to have like what we call alphas, which are the servers that that hold the data. You can have as many groups as you want. And in every group, you normally have 3 or 5 replicas, depending on the availability expectations that you have. And then the same for the zeros. And the zero is actually basically like I think it's called Kubernetes master or something like that, right? Like the controller that manages the whole cluster. That one also, we don't have one. You can replicate and have 3. So if one goes down, still the cluster is working.
Yeah, as you mentioned earlier, GraphQL. And I've seen GraphQL implementations that I was surprised to learn was kind of just, it was backed by Postgres.
Yeah.
But the interface is GraphQL. And like you said, JavaScript developers love that because, I mean, I think, there's something nice about being able to specify exactly the kind of data that you want back and nothing more. And also in quite a natural way because the GraphQL is kind of a JSON format, JSON-ish. So what do you think about that, having the graph interface into traditional databases? So
I think that GraphQL is a great alternative to REST. Like I really sincerely like it. It makes it so there's a schema. So when you're requesting things, you know what you're allowed to be requesting, but also at the same time, you also have not only the data, but also operations. So you have mutations and queries and things like that. So it's kind of like a nice modern way of doing gRPC. Like if you've ever used gRPC where you have the data, which is represented as protocol buffers, but then you also have all of the different services. They're called services. Yeah, all the different services, right? Mm-hmm. So it's kind of the similar idea for GraphQL, right? So that I like it a lot. That said, the problem is that it's a beautiful abstraction that is super hard not to make it leak, right? Like if you have a very beautiful abstraction of, it's all one graph, right? Like everything is a graph, everything, you're just gonna use everything as graphs. Okay, first problem, authentication, fun, right? Like if you start considering these things, there's actually many issues of implementing that in a very natural way. There's a lot of adapters. So, like Prisma, Apollo, and Hasura are examples of different companies that provide adapters on top of existing databases. That is great, right? Because it means that you can create a GraphQL layer on top of your old system, and then eventually, little by little, start replacing things and say, oh, this, I'm going to move it to this more GraphQL native environment, or I'm going to break this monolith into microservices and use federation on top. Like all of these things work and they're very useful. That said, every single time I go to a GraphQL summit, people talk about the same issues of caching, the N+1 problem. But like if you're fetching a lot of information and you're based on top of, a relational database, you're fetching all the data in the table, basically no matter what. So you're gonna be fetching that information, and then from there, you're gonna get a lot of data, and then before you send it, oh, guess what? Like on top of customers, now I want to get all of the orders. So you're gonna need to get those IDs and go down and get the information for the orders, and then go down again. So it's like that N+1 problem. And then in order to fix it, there's things like prefetching some things and like basically playing with caches and things like that. And it becomes really rough. It works, which is great, but it is hard to understand and even harder to debug, right? So that's why I was like, when it's for us, for Dgraph, right? Like GraphQL, it was super easy to adapt because our previous language that we support and we will support for a long time, it's GraphQL plus minus, because it's more or less GraphQL. And it's basically GraphQL, but adding some extra things to make it a better query language for a database, and then removing some things that didn't make that much sense, right? So adopting GraphQL was super easy. It's basically the same language. And now what we're doing is figuring out how can we bring the things that we added that make the language incompatible with GraphQL, how can we add them back to GraphQL in a compatible way? And there are ways, it's super interesting actually. It's like a lot of language design and APIs, but like inside of GraphQL, super cool.
Just because you mentioned debugging, in relational databases, for example, there's a huge culture around like, analysis tools. They can like analyze your query and so on. Do you have anything for Dgraph?
So not right now. We're actually working on having a query planner. Right now, the only places, like the thing is that the way the data is structured, query planners do not make that much sense except on how you use indexes, right? Mm-hmm. So that is where we're starting working, because sometimes using the index is not necessarily the best way to do it. It's basically like, if you have joins of two tables in relational databases. If one of them is much smaller than the other, there's better operations that you can do than just doing the full join, right? So it's kind of the same idea of like, depending on the size of the data sets, sometimes using an index is better. Sometimes just going and iterating over all the items might be faster. So that's a little bit the kind of thing we were looking into. That said, in the latest version that we published, we have a new thing that allows you to have an idea of how many nodes have been fetched, how many keys, how much data from the disk you had to get, how many network calls you had to go through. And then on top of that, I'm sure you'll love it, Jaana, we have open sensors absolutely everywhere. So it's like tracing.
Congratulations.
Thank you. It works surprisingly well. Like when you go into like, okay, so this is slow, what is going on? And you just open sensors and you can see all of the traces hitting the different machines, hitting the disk, and say, this was really slow, what is going on in here, right? Like that makes it so, the tooling that we're developing on top will be useful for the end user. But for any a knowledgeable person that already knows open sensors, there's a lot already in there. Thanks, open source.
It's also a knowledge tool. I really like distributed traces as a knowledge tool. Even you can probably it's so hard for everyone on the team to understand everything end to end. So like they can just basically use distributed traces to learn more about their project, right? Yeah. Yeah,
and that's also something that is like that is. Where I enjoy having control from, if let's say you're serving a GraphQL layer, right? You have GraphQL, that is transforming into things that are sent to the alphas and then talk to the zeros and then go to Badger and get something from an SSD. We own all of that code. So we're able to put open sensors across the whole thing and have a very clear view of what's going on. If you try to do something like that with an adapter and you have like an adapter over some other database, actually that integration is going to be super hard. So, the fact that we simplify everything and everything is kind of like built by us, it's everything in Go, everything open sensors, everything. I'm going to go with the word cloud native, right? Like the idea of everything is supposed to be running continuously. And if something crashes, whatever, just restart it and keep going, right? All of those things make it so at the end of the day, it is much easier to use because there's fewer moving pieces.
Somebody on Twitter the other day said Kubernetes was basically turning things off and on again at scale.
Yeah, and it works.
This episode is brought to you by GoCD. With native integrations for Kubernetes and a Helm chart to quickly get started, GoCD is an easy choice for cloud-native teams. With GoCD running on Kubernetes, you define your build workflow and let GoCD provision and scale build infrastructure on the fly for you. GoCD installs as a Kubernetes native application, which allows for ease of operations, easily upgrade and maintain GoCD using Helm, scale your build infrastructure elastically with a new Elastic agent that uses Kubernetes conventions to dynamically scale GoCD agents. GoCD also has first-class integration with Docker registries, easily compose, track, and visualize deployments on Kubernetes. Learn more and get started at gocd.org/Kubernetes. Again, gocd.org/Kubernetes.
We should talk a bit about what you wouldn't use a graph database for as well, because I think a lot of our listeners, and I certainly will be doing this. I'm going to go and play with this now because I want to really see, because I still don't have a kind of full understanding of from what we've talked about, really what this actually can do and what it feels like when you use it. But are there problems where you just wouldn't even think of using a graph database?
I mean, the way we built Dgraph was with, like general use cases in mind, right? Like you're storing data, like the same way you're using a document database. Document databases, you can use them for basically everything, right? So it's a very general field. We're trying to make it so, you can have graph algorithms and fancy things, but at the same time, the normal use case of just storing data and then getting it back and making sure that everything is stable and performant, that's what we're going for. That said, there are things like if you're doing time series data, right? There are much more efficient solutions for this because, it's a very specific field that has amazing solutions, right? So time series is one of those. I would say analytics is something that we're able to do depending on how much data you're throwing at it, right? Like if you're doing analytics in real time, I think that Dgraph is actually really good for that. If you're doing analytics on larger data that you're basically batching and just going over it, all the data at the same time, BigQuery is great, right? Like, why would you, re-implementing that is going to be really hard. So some tools are going to be better at some specific use cases. I do think that people still have a very clear tendency to use relational databases for everything. And relational databases are really great for, when you need to fetch a lot of information that it's always the same schema and things like that. Unfortunately, that's not the case that often. And, relational databases are somehow quite bad at storing relations, even though, it's in the name. They're not really good at that.
North Korea is called the Democratic People's Republic of North Korea.
I mean, yeah.
We are canceled in North Korea. Oops.
Oh, no.
Thanks, Matt.
At least someone in North Korea had sense of humor, That's something. Yeah, no, but it is hard to manage relations in a relational database sometimes. And that's why people enjoy document databases. It just makes it easier. You just store your data and that's it. And I think that graph databases could be, somehow like a substitute for document databases that's going to scale much better. So that's where I think it could go. Yeah.
Do you think that people are going to end up with running kind of different types of database in some cases, still having, probably if people are transitioning or if a team thinks this is a perfect use case for this, but we still have this existing system that we have to live with? Because you're not allowed to just delete everything and start again sometimes. So do you imagine that there's going to be situations where you would actually have your relational database or whatever your existing data store already is still running, but you also maintain the graph for those extra special specific cases?
Yeah, that's actually something that we see pretty often, where you already have a very large data set, and what you want to do is not get rid of that because you already have so many programs, so many systems already using that database, right? So replacing that database means that you need to replace all of the software on top of that, and that's a lot of work, sometimes impossible to do. But what we try to do in those cases is to get a graph database next to your traditional database and sync them together. So many databases are able to send like a Kafka stream of mutations so that, hey, this has changed, this has changed. So you can keep the graph database up to date completely with the relational database, and then use the graph database for the things that graph databases are good at, right? So traditional example, if you have, you have a blog system and you want to fetch all of the comments for a given blog, and that was big data, right? That is actually really hard if you store it as, a comment comments on something, and that could be either a comment or a post. Having to do that, you're going to have an extra index for sure, but you're basically going backwards into how relational databases work. So it's going to be really hard and not very performant. So you could use that to just keep the metadata of like all of the indexes inside of the graph database, and then fetch all of the nodes or fetch all of the IDs of the things that you want, keep that structure, and then the metadata of the text and images and whatever is still in your relational database. So using as an index database that is going to enhance what you can build rather than having to replace the whole thing. That's totally a normal thing, because if you go to a CTO and you're like, hey, I have this brand new database, replace yours with this one, they're going to be like, yes, no.
Yeah, we're just going to Control A and then delete on everything we've got. That's all right.
Just store your data in this floppy disk and then we go from there.
So if we actually if we poked around in the files that are stored by Dgraph, then what does it actually look like? I mean, what is it literally when it's on disk? What does it look like?
So you're going to see that there are 3 directories, P, W, and ZW, or ZW, depending on how wrong you say things in English. Z, yeah, I know. Zebra. So whatever, the P is where all the data is going to be stored. So you're actually going to have LSTM files. So basically what Badger stores. So it's a bunch of different key value stores represent an LSTM in disk, right? So you have a bunch of those. And then you have W, which is a write ahead log. So every single time an operation is sent to the database, we're going to store it there, just in case it crashes, right? So if it crashes, then we can tell, oh, this is where we were. These are the operations that we need to keep on applying, right? And then there's one more folder, which is the ZW, and ZW is the 0 write ahead log. So it's the write ahead log for the cluster itself. The zeros are the ones that manage the cluster themselves. So you're gonna have those 3 folders, and yeah, everything in there, it's just binary files. You could technically copy those and send them around and start a new database, but the problem is that these files are actually the way they work. They contain things like how many machines you have in your database cluster and things like that. So over time, if you change that, probably you're going to end up having crashes, and that's not the way to go. But we also have things that you can export all of your data to JSON or RDF, or even you have binary backups which store in protocol buffers.
Is a file system is the only way to store data, or can I just write an adapter to just send it to like some blob store somewhere?
So it needs to be, so the idea is that Badger, the key value store, is designed to work on SSDs. right? If you're not running on an SSD, it will still work, but it will be way slower, right? So the idea is that SSDs need to be there. When you're doing a backup, you can totally store that in cloud storage or whatever. That's totally fine. The interesting thing is there was actually someone that was asking about how could they do it to store all the data in memory. And there's something that we're doing for Badger, for the key value store, where we're going to have the diskless mode, where everything is stored in memory, and then you would be able to run everything on RAM, which is not a great idea for a graph database that's supposed to store a lot of data. But if you have something really small that you want really high performance on, it's definitely something that you could try.
Is it possible to use MFS, or do you have to write a new adapter?
Oh, yeah, it's already built, so it's what we're doing is not adding a lot of things. We're basically removing some checks that we had. Like there was some blocks that were storing disk and some small things that we had to remove. By default, we already have adapters to write everything directly in memory. You don't need to do anything.
That's cool.
So sorry, Johnny, if the data set, I don't know, I apologize to you because the listeners didn't know you had your hand up, did they? You've got to think.
Nope,
it's hard.
They didn't.
This job is hard. And to top it off, I've forgotten what I was going to say. So over to you, Johnny.
What a great host.
I'm telling you.
London calling. Okay. It's like there's a big delay as well. Although there isn't. This is amazing. Sorry. We'll cut this bit out. Sometimes I just get amazed that technology works. So this is one of those times. Johnny.
No, this bit will be left in, I promise you.
Anything where I look stupid stays in. That seems to be the policy.
So on episode 103, actually, we had some folks from Dgraph on the show. We had Manish and we had Carl Breyer, Manish Jain. And we talked about a lot of things, including sort of a ristretto. I'm sure I'm butchering that. Ristretto, like you can correct me when you when you answer this. But what is I believe the idea was to introduce like a really good cache that could serve sort of the needs of Dgraph sort of under the hood. I'm interested in hearing sort of the state of that transition and whether it's been done already or in how things are going, how things are performing. Kind of interested in hearing about that.
Yeah, so technically you pronounce it, if you want to go Italian, you go ristretto, but otherwise we say ristretto, and it's much easier. And so ristretto is this caching mechanism that we're integrating at different levels. So one of the levels is actually in the key value store. We're going to have an integration with Badger directly. And the idea here is that we've added encryption and compression to the key value store, which makes it harder on the CPU, right? So when you need to decrypt things before you can read them, that's the CPU taking extra cycles. So the idea is that by having a cache, we will make it be as fast as before by using a little bit more memory, right? Then on top of that, we're also adding it at Dgraph level, and we're even thinking about using it at GraphQL level. So then we could have like caching at many different levels and trying to see what is the most performant option, right? The interesting thing about ristretto is that running a cache and go is actually really hard. Like it is surprisingly hard. Questions like, if I give you a pointer to a struct that has a bunch of things, how much memory does it take in memory? Like how much space does it take in memory? That is super hard to answer.
What the point
is that? No, not like what is behind the pointer, right? Like you have a struct, but then of course is the sum of the fields. Sure. Plus aligning and things like that. And then what is the size of a map? It's the size of all of the keys plus some extra stuff. What is the size of a slice? Well, it's the array plus some extra stuff, right? So you get like plus some extra stuff in so many places that actually figuring out, given for instance, if you have a JSON file and you want to parse it and say with, certain accuracy, how big is this going to be once I parse it in memory? That is surprisingly hard. So when you're doing this for a cache, if you don't get that right, the problem is that you cannot really tell whether this new object fits in memory or not. So should you drop something before you load this one or not? It is hard. And even gRPC, it's like gRPC works really well, but gRPC doesn't really do this either in Go. For C++, there's this concept of arenas where you can decode objects directly into a memory space. But in Go, it doesn't do this. It doesn't support it, right? So all of these things like memory management in Go are surprisingly complicated, which is fun. But also, it's like, I've seen some issues that was like, I literally have no idea. I don't know how to help you with this. So good luck.
And of course, none of your old Google friends will talk to you anymore. So you can't even ask them.
Why am I here on this show?
That's a good question. My God. But yeah, all in all, it's like Ristretto, the whole idea is to make Badger better and Dgraph better and being able to use memory in a way that compensates for the extra cost in CPU. But also at the same time, we wanted to make it open source so anyone can use it for whatever they feel like it. And it's pretty successful. Like a lot of people have been adopting it, filing issues and feature requests and things like that, which is really nice to see.
Yeah, I'm actually using it now in a project.
Nice.
Yeah, it is great. And it's such a simple kind of API as well. So it's really easy to just plug in. And it's so satisfying when you suddenly your application just gets extremely fast. It's very satisfying. I don't look at the RAM. I'll just get more RAM if I need some more RAM. That's my approach. But others like to be a little bit more scientific. So how do you? I'll just spell that out then for anyone interested, and we will post these links in the show note. But it's Ristretto. That's right, isn't it? Ristretto.
Do you know what a Ristretto is, at least?
Is it a type of pasta? And that's not. I'm not being rude. I genuinely. It's made me hungry.
Because it sounds Italian, it's pasta?
No, I thought it was.
No, a ristretto is like a very, very short espresso. Oh, so it's like a tiny coffee.
Yeah.
Espresso's already tiny though, isn't it?
Yeah, so a ristretto is even smaller. Yeah, it's like couple drops of coffee.
It's
really.
Like an espresso for kids.
I think that if you feed your kids ristretto, you end up with someone like you at the end. Like, I would not feed ristretto to my kids.
Yeah, it's like the same amount of coffee. I think it's like same amount of coffee, but it's like shorter. So it's like really dense, right?
Oh, yeah.
Like something like that.
It's compressed coffee. Yeah.
Sorry, I got told off for suggesting it was pasta, but it turns out it's coffee. Come on.
I mean, but yeah, that's the whole idea is to make something very small that works well. So Ristretto is a good name.
Yeah, it is great. I recommend people try it. It's so easy to plug into your existing Go projects as well.
Indeed.
Thank you so much for educating us, Francesc. And what's the domain name for people that want to find out more about what you're doing?
So dgraph.io, so dgraph.io. And also before we finish, actually, I wanted to mention something. So there's FOSDEM coming up. You may have heard about it. This open conference in Belgium that happens in February 1st and 2nd, if I'm not mistaken. And this year again, co-managing it with Marge Eiskens from Women Who Go. So the CFP is open. So please apply. We want to have as many proposals as possible. So at the end, we'll get really good, high quality talks. They end up being given at a very small venue because the conference is always super crowded and it's fun. But then also we end up with a very nice video. So, even if it's your first time speaking, it's a great place to try it out. And also, you will have people helping you, mentoring you, reviewing your slides and helping you rehearse, whatever it needs. So, first time speakers, totally welcome and actually encouraged to apply.
Brilliant. Thank you very much. We will post all of these links in the show notes, so don't worry. And all that leaves is for me to say goodbye. Thank you, everybody. Thanks for listening. We'll see you next time.
All right, thank you for tuning into this week's episode of Go Time. If you're not yet, hang with us in Go for Slack. We have a channel called Go Time FM. Look it up, you'll find us. Hang with us during the live shows, connect with other members of the community, share stories, share code, share coffee recipes, whatever. It's a lot of fun. Also, we have discussions at changelog.com on every episode. Head to changelog.com/GoTime, find this episode, and discuss it with the community. Also, thanks to Fastly, our bandwidth partner, Rollbar for helping us move fast and fix things, and Linode for hosting the Changelog platform. Our music is produced by the mysterious Breakmaster Cylinder. And if you want to hear more awesome podcasts like this, subscribe to our master feed. It's one feed to rule them all, plus some extras that only hit the master feed. Head to changelog.com/master or search for Changelog Master in your podcast client. You'll find us. Thanks for tuning in. We'll see you next week.